Okay, so it's a great pleasure to have Ronnie van Meter here today for the CQT Colloquium. So Ronnie is at the Keio University at the moment, and he did his undergraduate studies at Caltech, then did masters at the University of Southern California, all in engineering, or I think first engineering and applied science, and then computer engineering. And then I think he worked for a couple of years in California before he came to Japan to do a PhD. And I guess that's when you went into quantum information. So the PhD at Keio University. And now he's an associate professor, or is that still correct?
No, I'm full professor these days. That's been true for a while now.
Okay, and yeah, so he wrote two books. One is actually a tweet storm that has almost the length of a book on quantum computing architecture, which I think has in it all the kind of references one would want on the topic. So this has been your PhD topic, I guess, and also afterwards. And the other one is what I'm reading right now. It's that
very nice.
Networking, and that's what the talk today is going to be about. So with that, I give you the floor.
Thanks. Thanks for the invitation too. You know, I wish I was there in person. I love visiting Singapore. I wish we were all in the same room somewhere, but you know, hopefully we'll do that sometime soon. Okay, let's see. You should be seeing my full screen here, and let's hope that Keynote and Zoom are going to be friends. You should be seeing my just a photo of Mount Fuji there, I hope. So I'm going to talk to you today about engineering the quantum internet. And yeah, there's the list of titles and more importantly, the list of collaborators who have contributed to a lot of this. So as Marco mentioned, I've been doing quantum computing stuff for a while now. And actually, right now, it's 17 years in classical computing systems and 17 years in quantum computing systems. So right now, it's 50-50. This is a picture of my group from last fall. That's us with Professor Jun Murai, who's the guy who brought the internet to Japan and me to Keio. And he's in the Internet Hall of Fame for the former, not the latter. And all the way at the top in the upper right of your image is Mikhail Hajicek, who I think many of you there in Singapore probably recall was postdoc there at CQT. And he's been with my group now just over a year. And boy, are we really happy to have Mikhail around. He makes everything better. So we are going to talk about networking today, quantum networking. I wanted to first give you the idea that there are a bunch of people in Japan who are actually working on this topic. The list of places in the upper left there is roughly people who are working on quantum key distribution, and the people on the right is roughly people who are working on quantum repeaters. I work almost entirely on repeaters. I don't really work QKD at all. But we have created a thing called the Quantum Internet Task Force here in Japan, QITF.org. There's a group photo from the first meeting, which I was actually absent from. And we have people who are working on every aspect of the problem. We have people who are working on the physical layer, the types of memories that we're going to use. We have people who are quantum optics and network architecture, people from the classical internet community, people working on security proofs. And so we're trying to build a very broad-based organization here with the goal of actually creating an actual test bed network of quantum repeaters over the next 5 to 10 years. So today's story, what are we going to talk about today? Well, first, a couple of observations. Number one, networks are more than just collections of components. And two, building these distributed quantum states is actually distributed computation. It's not like the store and forward mechanism of the classical internet. Then I'm going to talk to you about the quantum recursive network architecture, which is actually something that Dominic Horsman, Joe Touch, and I laid out almost a decade ago. And we laid out sort of our vision for what a network ought to be like, and then we sort of put it on the shelf with it kind of in the back of our minds. Well, it's now come time to really start putting the flesh on it. So I've brought that back out, and we're working on it as fairly actively now. Within the network architecture, one of the most important aspects is how connections are actually created. And this has actually formed a big chunk of the work we've done over the last 2 or 3 years. So I'm going to tell you about the rule set based operation and how we go about actually establishing a network connection, the messages that get passed from node to node and their contents. Now I'll tell you a little bit about the current work that we're doing, some of the graph state repeaters, and show you our simulation tool. And then finally, I'm going to ask you to get involved in this in some various ways. To CQT, that pretty much everybody is familiar with the basic ideas of teleportation and entanglement, and you probably know about quantum error correction as well. Maybe you've heard of 1G, 2G, and 3G quantum repeaters. Maybe not. That's not going to come up in particular in this topic. Excuse me, in this talk today. And I'm going to assume that you know the physics better than I do, but the network engineering probably not as well. So, posited. All of the hardware problems are solved for individual components. Our question is, how do you take those components and turn them into networks? And this is a view of our quantum internet simulator actually in motion. I hope that the animation is actually coming through in the video. We'll see if hopefully you all can see it. What you're seeing here is actually the topology of a network based on a real network that forms a part of the internet. And I'll show you a little bit more about that as we go. So how do we get there? So networks. This is a map of the ARPANET, which many of you probably know is broadly considered to be the most important precursor to the internet that we have today. Although last Saturday we had actually an anniversary celebration for the 35th anniversary of the first connection from Japan to what was called CSNet, which was actually an important network that was sponsored by the U.S. National Science Foundation in the United States. The ARPANET is a predecessor even to that. And so this map actually is a map of the state of the ARPANET in 1979. And that node that I just circled there, that's Caltech, where I did my undergrad. And then in the lower left, those are 2 nodes that were at USC's ISI, Information Sciences Institute, where I worked for a number of years. When I arrived at ISI in 1986, a map just like this one was actually on the wall at ISI. So we go from that map to a map like this. This is a map of the entire internet from 1999. But when you look at this, what you are seeing, the individual dots in this are not nodes in the network. The individual dots that you are seeing in this, each one of those is a network. You can't even draw a map like this today because there are so many networks that are connected together to form the global internet that we all use today, that a map like this would just turn into one large blob of color. So each of those individual nodes represents a network that looks maybe like this, or like this, or like this. All 3 of these are measured topologies of the individual networks that make up the internet as a whole. So one of these might be, all 3 of these, by the way, are very small networks relative to the size of those things that are mentioned there. But one of these might be, you know, the NUS network, and one of them might be the Keio network, and one of them might be the Wide Project network, or something like that. And of course, not only do we have that level of topological complexity and organizational complexity, but we also have to deal with the fact that the network spans the entire globe. And so we're talking about latencies on the order of 100 milliseconds to exchange a message from from Japan to California and back. So with all of that in context, the job of a quantum repeater network is to make end-to-end entanglement. Modulo some arguments about temporal matters, which Bill Monroe likes to sort of argue with me about. You know, he and I sort of, we like to sort of spar about that topic. And also, entanglement is a consumable resource. So the job of the repeater network is to make lots and lots of that entanglement. But this is distributed computation. The classical internet you're probably familiar with. The fundamental semantics of a packet. You have a packet or a message that gets sent from node A to node B. The fundamental semantics of that are that the packet contains a destination address. It also contains a source address, which is important, but the destination address and the semantics are that the receiving node parses that destination address and figures out how to send it on toward the destination. That's called store and forward. But for quantum networks, this really doesn't work. Loss and decoherence and gate errors mean that we are lacking in the scalability. It's not possible to go beyond just a handful of hops working in sort of the most direct equivalent to store and forward methods. So we have to compensate with it for this along the way. And this process is complicated and involves a lot of 2D classical messaging, including things like acknowledgement or not acknowledgement of the receipt of photons, issues like purification, issues like quantum error correction. And so the whole thing is in fact a distributed computation that takes place in semi-synchronous fashion among the set of nodes that are actually involved in my connection from here at Keio to you at National University of Singapore. So with that in mind, then the job of a quantum repeater, an individual repeater node, is number one, to make base level entanglement over a link with its nearest neighbors. Number two, to couple entangled links along a path to create the end-to-end connections that meet the application's needs. So to build a bell pair, for example, that spans across all of the hops between us. Number three, to monitor and manage errors via purification, quantum error correction, or both. And number four, then ultimately to participate in the management of the network itself. And that's one of the things we're going to talk about as we go as well. If that's the job of an individual repeater node, and we already talked about the role of an individual network, then the job of the quantum internet is to do all of this across a set of heterogeneous networks that are both physically and logically heterogeneous, and in an environment with minimal trust between those individual networks. So no knowledge of the internals of the networks that are next door, and in the possible presence of malicious nodes. So to put all of these kinds of problems in context, or to sort of examine all of those, my group over the last decade has planted a series of flags. So this is the campus where I work, the Keio Shonan Fujisawa campus, and that's the Keio flag you're seeing there. So we have planted a set of flags on different topics as we go. So some of those flags include, first, a network for the architecture as a whole, and I'm going to talk about that in a few minutes. We have worked on the protocols, meaning the set of messages that have to be exchanged and the semantics of those messages, and for example, what you do when those messages don't arrive and things like that. We have worked on routing in the network, figuring out what the best route is to get from, say, node A to C in the diagram there in the upper left. And we have worked on multiplexing in the networks. How do you manage the resources? With limited bandwidth, how do you share that bandwidth? With limited memory, how do you share the memory? How do you handle all of this? I believe, by the way, that this paper that we published in the Proceedings of the SPIE back in 2011 represents the publication of the world's first simulation of a topologically complex quantum repeater network. I should have the word repeater in there so people don't get confused about QKD networks. So we had done, and other groups have done, in years prior to that, simulations of chains of repeaters. So you go from node A to B to C to D to E in a single line. But I believe that work there represents the first simulation of a network involving multiple nodes and a topologically complex network. And also I would say, by the way, that the layered protocols represented by a set of papers, including this one in the Transactions on Networking in 2009, we've actually really sort of superseded that, and we have different ideas about how the protocols should actually work today. We have also worked on internetworking. How do you connect two networks together where the two networks are of different logical kinds of networks? So for example, if you're familiar with 2G networks depend on quantum error correction in the network rather than purification. And so how do you connect together a network that depends, for example, on the Steen 713 code to a network that depends on the surface code? So we've worked on that level of interoperability. We've asked the question, given the state of the classical internet with all of its security problems, what happens when somebody actually hijacks one of the repeaters in the network? Is that similar to what happens in the classical internet when someone takes over a particular router in the internet, or does it offer new capabilities for the attacker that might give them some sort of additional leverage that scales in some way beyond what you might normally expect? We've worked on what you might do with the repeater networks once they have built. For example, one of the proposals is to use quantum repeater networks for a concept called Byzantine agreement, which has a classical equivalent and is an important topic in distributed systems overall. Some researchers from Israel proposed a quantum version of this a number of years ago, but they didn't propose a detailed circuit for it, a detailed breakdown of how it would go. And we thought, well, this could be a good second application for a quantum network. So how hard is it to actually execute compared to QKD? And it turns out it takes more qubits and they have to be higher fidelity, and it takes more bell pairs to execute Byzantine agreement than we had originally hoped. And so it's going to take nodes of several hundred qubits, and it's going to take infidelities of 10 to the minus 6 or something like that. And so unfortunately, it's a harder application than we had thought, but that's the kind of analysis that we've done over the course of the last 10 years. And another one we've worked on is we've worked on network coding, which is a means for improving the utilization of resources in the network. And again, that has an important classical equivalent. So let me tell you about the quantum recursive network architecture, which Joe Touch and Dominic Horsman and I defined back in 2011. And we draw it, for example, something like this. So what you're seeing here is not a diagram of an individual network. What you're seeing here is a diagram of an internetwork, and one that's organized recursively. So for example, each of those dots might represent a node on the network, but in fact, as you can see in the upper middle there, it might be a recursive network where one of the nodes in the diagram at this level actually represents an entire network of itself. Then in the green ovals might be the boundaries of individual networks. And so this one consists of 1, 2, 3, 4, 5, 6, 7, say 8 networks collectively here. Now, we have seen already in the classic discussion of the classical system the topology of an individual network, and we have seen the topology between those networks, the internetwork topology, which is maintained in the classical world by a protocol known as BGP. All of this, if that's a two-level architecture in the classical internet today, the recursive network architecture allows us to recurse to an arbitrary depth, and we think that this actually works very well to meet the demands of the quantum internet as a whole. So let's look at what happens sort of at the application level. Let's say that I want to create a 3-qubit graph state with 2 other nodes in the network. So I'm going to carry the role of what we call the initiator. So that's me and the yellow circled there on the left, and the two pink nodes are responders in this case. People sometimes use the terminology when talking about quantum repeaters of source and destination. Even we're sometimes sloppy and we use it as well. But in fact, the quantum states that we're talking about, once built, are symmetric, and there's no obvious equivalent to a source and destination, meaning where the data originates and where it arrives at. So instead, we're using the terms initiator and responder to describe what happens to the network. So maybe the state we actually want to build looks something like this, where the gates there in the middle are controlled Z gates. Each one of these lines represents a qubit being held at one of the three nodes here. And they're subscripted with the address of the node and also the name or an identifier for the individual qubit, so that you can have multiple qubits in these things and you can talk about it, about the separate qubits that form the collective state. So if we know that this is the idea, we want to share this 3-qubit entangled graph state with these three nodes, the initiator and the responders, how do we go about creating it? Well, maybe this is actually configured into, here's a simple example of an internetwork. We've got 3 networks here, network 1, network 5, and network 7. And we've labeled each one of these nodes with an address. So now we know that we want to create the state shared between node 11, node 55, and node 77. And what we are going to do with this is we're going to take this actual internetwork and this network, the state that we want to create, and share it. But one of the first things we have to know is how the data is going to get from one place to another. So each one of the nodes has a table of information that we call a routing table. You're borrowing from classical network terminology. So this is the contents of the routing tables. It tells you if I get a request from somebody else and I'm asked to share it with node 52, how do I find node 52 or node 55 or whatever the network actually has, whatever actually is requested. So we're going to take this requested state and we're going to try to figure out how to build it across the entire network. What we're going to do is we're actually going to rewrite this in a recursive fashion, and the rewritten circuit for this, or the rewritten request for this, may wind up looking something like this, where, for example, in this particular example here, what we've done is we have rewritten this so that one node somewhere in the middle of the network is elected to create the 3-qubit state, and then we teleport the 3 component qubits, one to the left and one to the upper right and one to the lower right, to create the final end state. So with that kind of framework in mind, how do you actually go about building the protocols to do this? That's sort of the long-term goal here. So far, the only thing we have worked on in detail is, in fact, doing this for 2-qubit states for dealing with bell pairs end-to-end, but we've actually begun some work on this at the application level in collaboration with some other researchers to actually build those graph states as well. So why is this sort of key idea of this recursion and the rewriting of the states valuable? Well, we think it's ideal for internetworking, networking between separate networks. This will support heterogeneity because the decisions for how to achieve something are made locally. So the description process tells the network, I need a bell pair between here and there of a particular fidelity, but then the network itself is empowered to make decisions about how to route within its own boundaries, and to understand how many rounds of purification are going to be needed, or other sorts of questions similar to that. This also retains the autonomy of the network boundaries, so I can change the topology inside my network without having to tell everyone in the world what's going on in my system. It supports hierarchical routing smoothly, and it unifies the overall software implementations of this, which makes for nice, smooth network protocols as we go. There are a number of things that are hard about this, one of which is the fact that it is a distributed computation, and so figuring out how we want to do that's actually a tricky sort of thing. All of this, we need sort of a fully generalized mechanism for dealing with all of this, and so it's going to be ultimately a relatively complex system. But the approach that we have been taking for the last few years is what we call rule set-based operation of the network. And the primary driver, a lot of this, was my master's student, Takaaki Matsuo, who is now off probably making more money than I make working as a software engineer. But we are continuing to push forward this particular architecture. Within this, we are assuming that this is essentially the NISQI era, the Noisy Intermediate Scale Quantum Internet, NISQI era, which means that one of the things we have to worry about is we have to worry about errors in the system. And so this is just an overview of the many possible sources of errors in an individual link, let alone in the end-to-end network. But let's take a look at this in terms of how we might execute one of these kinds of rule set based operations. And for the example I'm going to use, let's look at tomography of an individual link in the network. So one of our links in the network is composed of both a quantum channel and a classical channel. And then the kind of stylized atoms that you see there on the left, they represent stationary qubits. We have Alice and Bob there on the left. And then the wavy lines in the middle represent our entanglement. So the first thing that happens when you turn on the link, when you turn on the routers that are connected to each end of the link, is Alice is going to boot up here, and Alice is going to send a request to Bob saying, we need to do some link level tomography on this so we can figure out whether or not this link is any good. Bob, in return, will send back an ACK saying, acknowledging Alice's request and saying, yes, let's do this. Alice will then prepare sets of rules. We'll talk more about the rules in just a moment, but roughly rules consist of two parts. They consist of a condition clause and an action clause. This is similar to what the software-defined networking people would call match and action, but we have called it condition and action. So Alice is going to be responsible in this case for making a set of rules for herself and one for Bob. And then she's going to take that set of rules that she defined for Bob and package them up in a message and send that message to Bob, who will then unpack the message. And now Alice and Bob both have rules that describe what is going to happen in the process of executing this tomography. And now they have an agreement on what they're going to actually achieve. The rules might look something like this. So here's a pair of rules that would be used for link level tomography coupled with one round of X error purification. And so there are two rules. The upper one is the X error purification rule, and then the lower one is the measurement rule for the tomography. Rule number one includes a condition that says when we have an entangled pair between Alice and Bob, that's the condition. We have an entangled pair between Alice and Bob. Then the set of actions is we're going to execute essentially this quantum circuit that's outlined in pink there. Then rule two is once you have that entangled pair after the purification, and assuming we've done this less than, for example, 3,000 times, then we're going to measure out the qubit in some basis and actually store those outcomes and exchange them so that we can calculate the tomography, so that we can conduct the tomography calculation itself. Each qubit in a node is actually waiting on the condition to be fulfilled for a particular rule. So there's a set of resources that are waiting on this particular rule. So in action, it will look something like this. Let's say we've got two bell pairs that have just been successfully built between qubits Q1 and Q1 prime and between Q2 and Q2 prime. What's going to happen is that those qubits will get assigned to rule one at each end. And in each case, the rule engine that executes all of this will recognize that the clause in the first rule, the condition clause in the first rule has been met. And so we can actually execute then the action in rule 1. So we'll actually execute that. And what is required in this will actually execute this circuit at each end. It's shown there on the left and right, which is the basic circuit for purification involving a C0 and a measurement and then some feed forward on it. While we are doing this, the first bell pair has to be, in software terminology, locked so that nobody else can allocate and use it for something else while they're waiting on it. So these circuits will get executed at each end. The entanglement in the second bell pair goes away, and assuming that the entanglement, the purification is actually successful, the purification results are actually exchanged, and now Alice and Bob can confirm that they found the same value and that the purification succeeded. And now they can take those qubits and promote them from rule 1 to rule 2. Now, with rule 2, we can check, and what we'll find is that, in fact, the condition clauses for rule 2 have also been met, and so the qubits at each end are actually measured, and the tomography process is actually conducted. Ultimately, you could, so then the tomography results also get exchanged between the left and right there. And now each end can actually calculate the density matrix, and the density matrix that results from tomography you might describe using a flowchart that looks something like this. So that gives you, we've covered sort of the basic idea of the recursive network architecture. And I've shown you sort of the basic idea of how rule sets are defined and how they are shared and how they operate, the sort of the condition clause and the action clause for each of a potentially large set of rules in doing things. Now, how do we actually go about creating a connection in a more complex network? So let's say we've got a network that looks something like this, and our goal is to distribute end-to-end bell pairs between S and D. So S is going to be our initiator and D is going to be our responder. And let's say that's that S is John Preskel's house. So he wants to connect to the Quantum Universal Engineering, Networking, and Computing House Incorporated, or QUENCH. And all of the nodes in between, A, B, and C there, are going to be responsible for doing entanglement swapping and some sort of error management, possibly including the purification. So there are several stages to the problem. First, we have to select a route, which I'm not going to talk about today. Then we have to plan a sequence of operations for each of the nodes along the network or along the path. And then we have to also convey the sequence of operations to those nodes in the network. We are assuming that the links are heterogeneous, that is, they're not all the same, and we don't know very much about them when we actually start. And for the moment, we're putting aside multiplexing. We're putting aside the issue of the resource management in the system as a whole. So each node has a certain amount of information. It knows about its own capabilities. It knows about the links that are connected to it. It knows a little bit about the neighboring topology, but not a whole lot. And it knows how to get from where it is right now to some gateway that takes it to the larger network, out into the larger world. In the words of Obi-Wan Kenobi, congratulations, you've just taken your first step into a larger world. But they don't have a certain amount of information, each individual node. They don't know all of the details of the quality of the memory in other nodes other than themselves. They don't know how many qubit memories each node in the entire network has. That would be silly. They don't know about the local gate fidelities for other nodes, and they don't know anything about the internals of other nodes in the network. So in fact, the path from John's house to Quench might look something like this. It's going to pass from John's blue network here in the left to Quench's green network in the upper right, and it's going to pass through all of these nodes in the middle. And the structure of each of those nodes in there in the middle, all of that is opaque, not only to John, but to every other node that's on his blue network there initially. So how do we go about dealing with that? Well, I'm only going to talk today about how we structure this inside one single network, but from John's house to the gateway to the outside world, we're going to pick some sort of network path here going from left to right, using some sort of minimal amount of information as we go. And the way we're going to get there is first, from John's house, the node S is going to send a request. It's going to send a request along the path. The first thing it's going to do is add information about the link between itself and its first hop to this request. It sends it to A. A adds information about the connection between itself and node B. It forwards the message on to node B. B adds information about the connection between B and C, sends it on to C. And then this process goes on to D, and then it repeats until it gets to the gateway I at the outside. The gateway I now has all of the information that it needs to plan the entire connection between nodes S and I. Okay. It now knows about the data rates, how many bell pairs per second, and the fidelity of the individual connections, and the gate fidelities, and it can plan a set of operations between here. Where are we going to do entanglement swapping? How many rounds of purification are we going to do? What sort of data rates do we expect? How do we get to a fidelity of 0.98 for the requested states between S and I? So it's going to create a table of these rules. So each line you're seeing here represents a rule set that is sent to each of the nodes along the path. And so some nodes will have a single rule, some will have multiple rules. It sends this set of rules to H. H takes its own set of rules off of this list of rules and sends the set of rules on to G, which removes its own set of rules, which sends it on to F, which removes its own set of rules. E removes its set of rules. D responds. And so this process continues with each node getting its own set of rules all the way as you go. And ultimately, every node between S and I now knows how it's going to create to participate in the creation of entangled bell pairs between the nodes S and I. All right, that is our view for how a network is actually managed and how those connection setups are actually conducted. So you have we have the basic recursive architecture. We have the rule set based structure, and we know how the rules are actually created. They are created in this sort of hop by hop fashion with a stack that actually conducts these things, and that allows also I, which sits at the boundary there between the networks, to then do an equivalent planning procedure going across the next network, going across each of those pink networks to get from its location to John's house. All right, so that's our vision for the quantum internet as a whole. One of the particular tasks that we're working on right now is actually how to create graph states across the network and how to use them. Here is one of the tasks we're actually working on. We are attempting to create a network where we have simulated networks, a large simulation of a quantum network where all of the links in the network are simulated except for one network that actually uses symmetric parametric down conversion to create this. And so we'll have this sort of emulated network where 99% of the network is simulated and 1% is real. And Mikhail is actually leading that work for me. So these graph states can be used in several different ways. They can appear at the link level or at the network level at the bottom point. So this is actually where we're using graph states to create bell pairs on an individual link and then ultimately along an end-to-end path. And that's what we're working on primarily right now. But we can also look at application level use of those multi-party states, the graph states and whatnot, which are like the example that I gave you in the QRNA example earlier. So, applications might use graph and W states. The systems make use of this. And our goal for all of this is to achieve a certain amount of realism for this through a combination of experimentation and simulation. So our simulator looks something like this when it's actually running. You saw one rough element of it a minute ago. Here's a simpler, or earlier in this talk, here's a simpler view of it with just a few nodes and links. This is, internally for us, this is our 4th generation simulator. This is the 4th time we have done a scrap and build from scratch on doing this. And we call this one the Quantum Internet Simulation Package. And not only does it work for those smaller networks, but it works for larger networks that look something like this. So now you can see these black dots that are moving across the network here. These are the connection setup requests that I showed you earlier. The blue and pink dots are either acceptance or rejection of those connections, depending on sort of what else is going on the network. And you can see how that goes. And then once all of the connections are set up, then everybody starts sending their photons around. The yellow dots represent synchronization timing pulses, and then the white and red dots represent the transmission of individual photons, and then the light blue ones are the results of the classical messages for the control, telling you whether or not, for example, the Bell state analysis succeeded. So this is sort of where we are with the network as a whole. There's a lot that's built, and there's still a lot to be done. We can scale up, continuing from there. This is the animation I showed you at the start of this. This again is a network that is derived from an actual network that's actually part of the classical internet today, and so you can see that these networks get to be relatively complex topologically, and our goal for this is to continue working in this. So our performance targets for this simulator are that we want it to work for 1G, 2G, and 3G networks. And we want it to work for a quantum internet composed of 100 networks, where each of those networks might contain 100 nodes, and each of those individual nodes might contain as many as 100 physical qubits. And so our goal here is to do simulation of systems that consist of up to 1 million qubits, where maybe as many as 5,000 of those qubits might be participating in the creation of a single entangled state. So that example would be using the 2317 Golay code across 100 hops in a 2G network. Now, obviously, if you're going to do a simulation at that kind of level, you cannot do even a state vector-based simulation, let alone a full density matrix-based simulation for the network as a whole. And so, in fact, the simulator operates in what we call the error basis, which is like the scalable quantum error correction simulators, for example, that are used for surface code simulations. This system is incredibly configurable. You can configure every link to have any length or latency and any error rate and any photon loss. You can modify the lifetimes of individual qubits in the network if you like. Everything is completely configurable about this. We have sort of some reasonable defaults, we hope, for a number of things. Ultimately, what we're trying to achieve with this, of course, is not just to sort of build something to be building something, but to actually use this to answer some important research questions. And the first on that list is emergent behaviors. What is it that we don't know about the behavior of quantum networks? In classical networking, one of the important discoveries once the internet itself reached a particular size is what's called congestion collapse, where the network itself starts to get so busy that people continue to add more traffic in retries to actually use the network, and the congestion increases, and the network winds up essentially collapsing. So what's the equivalent of that in the quantum world? These protocols we're talking about are very complex. the designs we're proposing here, are they complete and are they robust and will they work in the real world? We're trying to establish that to the best we can by use of these simulations and also some real implementations of some of these things. We're trying to understand different approaches to doing connections, including these the graph state-based approach that I talked about. You'll read in some papers on quantum repeaters, you'll read equations that show you an analytic approach to particular small networks. That works for very small systems or for a lot of simplifying assumptions like heterogeneity and 1 or 2 qubits in an individual node. When you get to the kinds of systems that we're talking about here, there's no easy way to create an analytic expression that would include all of the possible parameters for this. We would also like to know how these networks behave dynamically. When you change the conditions on a network or when links go up and down, sort of what happens with all of this. So that's what we're trying to achieve with this simulator we've built. QUISP itself was released as open source on April 5th of this year. The license in it is a commercial-friendly 3-clause BSD license, and you can find it on GitHub or by looking at our own website there. And so that's it with the simulation. Now, part of the reason I'm here is, of course, to share what we're doing with you all, but also to ask you to join us in doing some of this work. I am co-chair with Wojtek Kozlowski from TU Delft of a group called the Quantum Internet Research Group, or QIRG, which is part of the Internet Research Task Force, or IRTF. We have about 300 people on the mailing list in this, but the mailing list is generally pretty quiet. There are a few messages a month most months, except when we are leading up to the upcoming meetings. And in fact, the next meeting, hang on, let's see, so there. The next meeting is November 16th for about 2 hours. The IRTF meets in conjunction with the IETF, which creates the network standards for the internet. Those standards are what are called RFCs. We are beginning some work on those kinds of things in the QIRG as well. And the single most important thing that we're working on right now is actually a document called Architectural Principles for a Quantum Internet. Wojtek actually initiated that and he's leading it, but a number of us are now contributing to the document as well. And finally, I am an associate editor on the IEEE Transactions on Quantum Engineering, and we have a special section on the quantum internet. So if you're writing papers on how to do quantum repeaters or other aspects of networking, we are very happy to have those at the journal. And that's about it. And as Marco showed you my book, I guess I'm the author of the world's first book on quantum networking. And with that, the slide here says Honjitsu wa shuryo shimashita, so today is over, or the kind of sign that's put out by a restaurant when they have stopped serving for the day. So I think we are doing pretty well. I can't see a clock. Yeah, actually, we're actually on pretty good time here. It's 7 minutes till, and I'm open to taking questions. Marco.
I think there's a question in the chat. Maybe you can check.
Yes, I'm just looking at it right here right now. Let's see. For the benefit of the recording, I'll read this. Let's see. Hi, Mr. Rodney. Just wondering, in the internetworking setup for the classical and quantum channel, do we need to be concerned about the latency of the classical network, for example, TCP/IP? In quantum network, is there such a thing as latency is similar? Yes. If latencies occurred, what does it do? Overall, yes, those latencies are ultimately very important. With the connection setup process that we've defined, that connection setup process itself can be slow. It's done, sort of slow, as in, it would be okay if it took, half a second or a few seconds, because it's happening only when the connections themselves are actually established. But then there are lower level operations that need to happen in at least what we would call soft real time, like you want them to happen within the next tens or hundreds of microseconds. And that's one of the driving factors behind our decision to create the rule-based architecture. So the rule set-based architecture allows the nodes to have the maximum amount of independent decision making. And so in those, we can define when these conditions are met, you can execute this action knowing that the nodes and the other nodes that are part of the connection as well will be making decisions that are consistent with that. So the rule sets are designed to allow us to create consistent actions along the entire path, minimizing the amount of classical information or number of times that you have to wait for classical information, and thereby minimizing the amount of decoherences as you go. So the connection setup itself can be slow. The rule set based operations should be at least soft real time. They should be, microsecond level stuff. And then there are the synchronization pulses you need in the actual optical channel when you're heralding the photons and turning on your detectors and things like that. And those are, hard real time nanosecond level pulse controls. And those we are mostly leaving to the physicists. We're not worrying about that level of operation. So I hope that answered the question. I see James has popped up here. A further question or a follow up on that? We can't hear you. It does not look like you're muted, so it's probably a connection or a mic problem there. Okay.
Yes, maybe a related question to that. So when you say, so some of these rules, I guess to verify that the condition is met, you need information from the other nodes to decide that, right? So I guess the latency.
So there are times, yes. There are times when part of your condition clause is wait for a message from a partner node, and if the content says A, then do B. If it says X, then do Y. So yes, there are times when you do that, but the rule set based architecture gives us the framework for operating asynchronously whenever possible and being synchronous when absolutely necessary.
Yeah. So you mentioned about the latency tolerance today that you have experienced is in terms of microseconds instead of milliseconds.
Sorry, the latency where you're capable of tolerating is.
Yeah, that's right. It's you mentioned it's recommended to be within the range of microseconds rather than milliseconds.
Yeah, probably.
Okay,
that's very rough.
Well,
that's part of what we're trying to do. Sort of on the order of executing a few functions in an ordinary CPU, right? Yeah. Because the lifetimes of qubits that we're going to need for this, we're going to have decoherence times, T1 and T2 times, on the order of, ideally seconds, right?
Exactly.
Certainly at least milliseconds, but ideally seconds in order to make this work. And so we would want to make those decisions and go on to those operations, not like wait until tomorrow and execute this, but software runs on a processor, and as soon as that processor can make the decision, then go.
Right, sure. So I mean, at the end of the day, we want to get the consistency, the consistent result, as you mentioned.
Exactly.
Okay. So yeah. So because
I can kind of imagine that maybe eventually somebody might take those rule set kinds of things and implement it in an FPGA or in hardware some way, shape, or form, and that would reduce the latency from microseconds to nanoseconds. But that's way off in the future, and at the moment, it doesn't appear to be necessary.
Okay. So as you know, for 5G, I think the 5G, I mean the standard of 5G is less than 1 millisecond. So I always wonder, so how do you think 5G can help to support quantum networking development? I mean, do you think that 5G will play a part or an important role in terms of quantum networking?
Sorry, do I think 5G will help?
Yes.
In what way?
Do you think that 5G can help or support quantum networking developments today? Because I think the 5G standard for the latency is less than 1 milliseconds. So with the low latency kind of characteristic of 5G. So I'm just always curious, how can we make use of 5G technology or even 6G in the future to help to complement with what we are doing today?
I'm part of the WIDE project, which is the group of people who brought the internet to Japan, and a number of our researchers are very excited about 5G, and they're actually working on deployments of 5G networks here in Japan. But it's outside of my own area. I haven't really looked at 5G very closely.
Oh, sure, thanks.
For what we're doing here, we are assuming right now that all of these connections are actually via fiber. And so as long as you're talking about the fiber for the quantum transmission, you might as well send the classical information down that as well. So we are expecting that the path and that the latency are essentially identical for both the quantum and classical channels. So I should emphasize, by the way, I assume everybody here realizes this, but we have occasionally had people get a little confused. I mentioned the 1G, 2G, and 3G networks for quantum stuff. Those are definitions of types of quantum networks and have nothing to do with the 3G, 4G, 5G mobile networks.
I see.
So it's easy to get confused by that because the terminology is the same, but they are in fact different.
Okay, so in the quantum network, we do have 1G, 2G, 3G generations.
Yeah.
Oh, okay. I didn't know that. I have to read that out. Thank you. Thank you for the insight. Thank you so much.
Classical cell phones, 1G was analog, and then 2G was TDMA, the first generation of digital cell phones, and then 3G was the first, sort of relative first ones that provided a real,
right, sure,
real internet connection on top of the cell phone network.
Sure. Yeah, my background has always been the service provider. I mean, I started my career from 3G up to 5G right now. Yeah. So it's lots of terminology and lots of things to learn. Yeah.
Before my last job before switching into doing quantum computing stuff was I was actually an engineer for Nokia, and I was actually an operating systems engineer for the boxes that are called the SGSN and the GGSN, which are two of the network nodes that are part of 3G networks. And even back then, so this is 18, 19 years ago now, people were talking about what they called all IP architectures and moving away from the mobile specific sorts of things and turning the mobile networks into more of a general kind of network. And 5G seems to almost finally really be there for what that vision was they laid out 18, 19 years ago.
Yes, that's right. Yeah, definitely. For 5G, it's pure IP network, but I mean, it's still classical. Yeah. So I just wonder, what would be the use cases, or is there any use cases, or even any experiments that has been done in the world, for both 5G and quantum network? So that's something I don't think I have really seen any much use cases on the internet yet.
Yeah, I haven't either.
Okay, thank you.
Marco?
Exciting. Yep.
Okay, yeah, are there any other questions? Lorenzo?
Yeah, just curiosity. I'm wondering why. So, which is the main aim of quantum networks, and why we are trying to communicate qubits?
I have an entirely different talk about that, about the applications for the quantum internet. I used to actually make it part of a talk much like this, but there's so much material that it's really two separate talks. I divide the uses of a quantum internet really up into three areas. One is security-related applications, the first of which is quantum key distribution, which can be done today using single photons, but with a certain number of significant limitations. As we build the real quantum internet, that will remain an important application.
Yeah.
The Byzantine agreement that I mentioned is also one of that class of security-related operation. The second category is sensor networks, and there are a number of people who are working on how to use distributed quantum states as exquisitely sensitive sensors for measuring magnetic fields or measuring gravitational fields, or as reference frames for doing things like high precision clock synchronization and things like that. So there are a number of those sensor related issues. The big challenge with sensor networks is, does the supporting classical hardware, in order to make this work, actually have to be even better than the advantage you get out of the quantum systems? So that's a tough question to answer.
Yeah.
And then the third area is just distributed quantum computation, much like the ARPANET and the internet itself was originally designed to allow people with small computers to connect to and use large mainframe computers. The quantum internet will have that same kind of driving reason to exist. One of my very favorite examples, one of my favorite ideas for the last 15 years is blind quantum computation, in which you can ask a server to conduct a computation for you, and the server learns nothing about the input data, the output result, or even the algorithm that's being run. Nothing except an upper bound on the size of that algorithm. And in order to do that, you have to have a quantum connection between you and where that quantum mainframe actually is. I love that idea. There have been several advances in it for reducing the demands that will be placed on the network and on the machines on each end, but there's still quite, I think, room for a lot of innovation in that will make it a lot easier to use and an even more attractive application.
Yeah, very interesting. Thank you.
So it's an excellent question. I did not include that in today's talk just because there wasn't time, but I can talk about that one for a long time as well.
Yeah, I know. Sure. Thank you.
Okay, do we have any other questions?
Yes. Any other final questions, comments, complaints, criticisms, announcements, advice, banter, burble, bicker, brouhaha, balderdash?
Well, I mean, one question, I guess we can keep our discussion going later on, but so one question I have is how, I mean, what you're doing is quite abstracted away from the physical layer, right?
We're trying to bridge that gap and trying to look all the way forward to what the quantum internet needs to be. But our experimental experience is limited, but it's actually growing.
Okay, but how far do you think we are away from this being deployed?
It's a good question. I started making repeaters one of the primary focuses of my own research really in about 2009. And one of the reasons for doing it was, of course, because I'm now working in a group that has tremendous classical networking capabilities, but also at that time in 2009, it's like, man, building quantum computers is so hard. Maybe building quantum networks is going to be easier. Let's go find out. And it didn't actually really take very long for us to realize that's kind of naive. And in fact, building quantum repeaters is arguably harder than building quantum computers, because you basically have to have sort of a modest scale quantum computer, plus you have to have all of the optical capabilities, and you have to have long memory lifetimes. And so hardware wise, it's a significant challenge, but man, there's so many groups that are making such tremendous progress on each of those components. On that slide where I at the beginning, where I said, I'm assuming all of these problems have been solved. In fact, every single one of those has been demonstrated in the laboratory. Are they of the level of robustness and performance that you would need for actually building systems? Not really yet. And even more importantly, they don't all go together very well yet. But the hardware people are making good progress. I think we will see what we would call real quantum computers in the next, real quantum repeaters. I think we'll see within the next 2 to 3 years. Obviously, the Delft group is the single most likely to demonstrate something that we would say passes those basic criteria. But it's going to be probably a good decade yet before we really have reasonable scale networks and they perform at some level in terms of both bell pair creations per second and fidelity that actually exceeds even the basic capability of just sending individual photons down fibers. It's going to be a while yet before we get there.
Yes. Okay. Thanks a lot. So if there are no further questions, then I would thank you again for giving us this really nice talk. And
I know I hit you all with a fire hose of information, but I'm trying to get through just a few key ideas and then supporting information for those key ideas. So I hope everybody got something out of it.
yes.
Great session. Thank you. Thank you, Ronnie. Thank you, Marco.
Thank you all.